So this is Hiroshi from Okayama University. Today I would like to talk to you about our study, analytical solutions for the number-density field of non-interacting non-plastic particles identical to the temperature field in a post-Taylor benchmark flow. So I will show you introductory part. Uh, Nanoparticles, particles measuring less than 1 micrometer are invisible, and their presence in seawater constitutes a form of marine pollution that endangers both uh, aquatic ecosystems and human health. So there are analytical flow solutions and low Reynolds numbers, such as simple shear flow, characterized by a uniform velocity gradient in both space and time, and the Terra Green Vortex analytical solution. Also, fine particles, such as nanoparticles, frequently carry such surface electric charges, thereby exhibiting a pronounced propensity for aggregation. It is important to illustrate how hydrodynamics influence such aggregation. This study aims to illustrate the relationship between the number density field of single and non-plastic-like particles whose characteristic size is smaller than characteristic scales of the flow, and the temperature passive scalar field. So let me show you about the analytical solution. So this study focuses on the two-dimensional Taylor analytical solution uh, with a corresponding velocity pair as follows. Here, T and R denote the non-dimensional time and Reynolds number respectively. The differentiation of the foreign string function is required to obtain desired results. In this flow, the global kinetic energy is characterized by the following equation. Here, this is denoted the sample average. The common equation that admit this two-dimensional analytical solution can be separated into two independent balanced solutions for fields of velocity, vector, and pressure. As demonstrated by these balances in the solution, the temperature variation of the flow is exclusively attributable to viscous diffusion. The linear forcing method has been reported utilized in the context of maintaining statistically stationary turbulence. In linear forcing, a body force term proportional to instantaneous velocity period added to the momentum equation, thereby forcing the flow in physical space. In this study, the property that the Taylor solution, the viscous term is proportional to the velocity field is explored as follows. Here, the linear forcing body force is prescribed as follows. It is evident that in the context of this forcing, the viscous term that emerges involved the two balance relations is considered null and void. This in turn results in the subsequent elimination of the unsteady term. The velocity field is thus regarded as steady as follows. In a given flow, the normal temperature of a concentration field generally satisfies the advection diffusion equations as follows. Here, PE denotes the Becquerel number, which is denoted that P is equal to the Becquerel number. The linear forcing framework adapted to the Taylor solution is used to specify the source term S in the advection diffusion equation as follows. Substituting the steady Taylor velocity field obtained above, the proceeding in analogy with the momentum equation, the source term can be chosen so that it cancels the diffusion term. As a result, the temperature field is obtained in the form illustrated in figure 1. And this figure shows the field uh, this term describes a particular number of dense fields, temperature field, and concentration field in a steady state two-dimensional Taylor analytical solution for a field of scale to phi. Here, this field coincides with the streamline field. The focus of this study is not particles. Particles measure less than 1 micrometer in diameter, which are considered significantly small for any interparticle interactions to occur. Further, due to their size, their particle response time and Reynolds number are considered negligible. Consequently, the consideration of the history term in the Maxwell-Reed equation can thus be neglected. Assuming a density ratio close to unity, gravity can also be neglected. In the long-term limit in which the sweep velocity vanishes, the governing equation for the number density field N over single non-particle spaces takes the following form. Here, N denotes the particle number density. Using a continuity equation for incompressible flow, the above equation reduces to as follows. As evident from this equation, the number density equation is closely related to the heat mass transport equation. The left-hand side is remarkably identical to that of the advection diffusion equation for temperature passive scale. Consequently, the number density equation can be regarded as an infinite Planck or infinite Schmidt number limit of the advection diffusion equation, in which the diffusion term vanishes. In this study, the Taylor analytical solution with linear forcing source terms there is the temperature or concentration field independent of the Planck or Schmidt number. Therefore, by replacing the normal temperature or concentration field with the normal particle number density, analytical solution for the particle number density field in the linear forced steady Taylor flow is obtained as also demonstrated in the figure. This one. To ensure non-negativity of the physical number density, this is written as follows. So let me conclude our study. The relationship between the number density distribution of endured non-interacting non-particle spaces and the temperature passive scale fields is quantified. The temperature and concentration fields also satisfy linear equations under the same flow configurations. The two-dimensional Taylor flow examined in this study utilizes the viscous term proportionality to velocity to introduce linear forcing. The particle number density equation reduces via incompressible continuity equation to the same advection form as the passive scale. The application of this study's framework to the particle number density equation utilizing the normalized formulation yields a closed form solution similar in shape to the temperature and concentration fields. That is all our presentation. Thank you so much.